I'm hoping that I can just continue on. It's recorded anyway, so please just don't tune me out. So,
Why didn't they give us that mark? Why do it Oh.
all right. Testing. Hello. All right, so we might as well get continuing on with our lecture material today. Cue recording if we aren't already. People are still writing. Thank you. So, last time we were talking about interrupts. We finished off the material on timers, and we were continuing on to talk about interrupts. The interrupt, of course, is a mechanism by which the normal flow of program execution can be interrupted by either an internal or an external signal. Today we're going to be talking about the manner in which the processor handles these interrupts at an architectural level. We're going to be talking about the process by which the existing information related to the existing processes is stored, and how the interrupt interrupts it, and how that's restored afterwards. Good. So, we sort of left on a question last time. What the blooming heck is a nested vectored interrupt controller? So, I brought the textbook with me this time. So if we have any questions, we should be able to refer to the textbook. How many people brought the textbook with them? Yeah! Digital. Ah, that doesn't count. It doesn't count unless it hurts you to carry it around, you know? Anyway, so with respect to... So let's just briefly recap the whole process, right? So we have main's execution is chugging right along. An interrupt request occurs. We're going to examine the mechanisms by which interrupt requests occur. We then service the interrupt service routine until such time as it terminates, and then we resume main, right? Or whatever, it doesn't have to be main, whatever function is operating at the time. So, good. So the process in detail, in our main program, we're going along inside of whatever function we are, whatever function we're executing. Whatever function we're executing will be on the stack, right? A lot of this will have to do with the system call stack, right? So what happens is at the point when the interrupt signal is detected, we look up the address of the starting instruction of the interrupt service routine in the interrupt vector table. So this is what the interrupt vector table is and does, right? It's actually stored really, really close to the origin point in the memory. It's the first byte after the actual first byte of memory. That's the beginning of your interrupt vector table, right? Each address inside of that memory space will map to a fixed address space elsewhere in instruction memory where the interrupt service routine for that interrupt is stored. So, when you write an interrupt service routine, it isn't just dropped into instruction memory willy-nilly. It isn't, just shoved in there. It has a specific spot and a specific point at which it is inserted. That way, the controller knows where to look for it. Any questions about that so far? Shoop. Good. So essentially, the current state of the program is saved. We look up the particular interrupt which we have received. We look up the starting address of that interrupt service routine. We load that into the program counter, right? And then we begin executing that code. We execute that code until that you hit a return operation or the end of the function in the normal way that a C program exits a function. We then restore the values of the various registers that were interrupted. We restore the state of main execution and then continue on until the next interrupt is received. So at a sort of top level general, I'm sure I've said this before in a different class, but the general design approach when you're designing something with interrupts. There were some questions early on in the class, why on earth would you want an infinite loop inside of code, inside of hardware? And the answer is, if everything that you need to do can be done with interrupts, then an infinite loop that does nothing is the perfect way to keep the main frame alive so that it's available to service the interrupts. Right? Make sense? Any questions so far? Good. So that's kind of your overall view. So one of the operations that occurs when we are loading from main into the interrupt service routine is what's called auto-stacking. Essentially, the states of certain general purpose registers, R0 through R3 plus R12, LR, what's LR stand for again? Return register. It's the return register. I don't know why it's called LR, but anyway, the program counter and the PSR register. All of these are loaded on, they're all pushed onto the stack so that they can then be retrieved when execution returns to the main function. So, like, the question at an architectural level, to some extent, is, we know that the C compiler will optimize our programs to a certain degree by using register memory. We also know that if we're programming in assembly, the registers are very important. The state of the register memory is very important. So this is, functionally, this is what needs to be saved in order to be able to return to main and return to it in the same state that we left it. Of course, the most important, possibly, of those is the program point counter, because if you don't know where you exited, you don't know where to get back to. Question?
Quick question. So, if an interrupt is triggered quicker than the signal of the timer, will it not be captured? Like if it's on and then off within the clock cycles?
Yes.
It won't be interrupted basically.
That's correct, yeah. So the question is, if you receive, so let's assume we have our processor. It's receiving interrupt signals. Let's assume that this interrupt, let's say we're waiting for a rising edge, right? Let's assume that this, where's chalk? If our, and this is kind of this is an edge case that you're talking about, but you knew that this was an edge case, that's why you asked. So if our clock signal is coming in looking like this, right? Let's say that we have an signal for an interrupt that comes up and then back down again. Something like that, right? Typically, edge detectors will detect state changes on clock cycle rising edges. So what we have here is a situation where the signal has blipped up and back down again between the 2 points at which it would have been sampled. So yes, in this case, this would go undetected. So yeah, typically if this thing is generated by a, a hardware peripheral or something like that, you don't have to worry too much about this because, they'll be aligned to the clock edges and everything will be fancy and nice. This is like, if you were like doing some kind of analog circuit, this could be a situation that you might see. But the other thing to consider with like a circuit like that, if you have a signal that's that short, does that even indicate the interrupt that you want to detect, right? Like, something like this could happen just from like EMFI noise, EMF, electromagnetic interference, right? So yeah, so there you go. Good question. So the interrupt service routine vector table, it doesn't just give you the memory addresses at which you'll find the interrupt service routines, although that is a critical function. It will also tell you what priority your interrupts have. So interrupt priority is actually not too difficult to understand. When you understand, first you must understand that all of the interrupts that you have for a particular board, like your STM32L4s or whatever the number is, they're all predefined and you can't define any new ones. So you have to use the ones that are given to you. That being said, you can also, like it's not as inflexible as I just made it out to be, but the interrupt codes themselves are fixed and can't be added to or subtracted from. The first 16 are system interrupts. So they're software-generated interrupts that the CPU will generate itself. These tend to be things like, I have detected a hardware fault, I have received a reset signal, all these types of things. Incidentally, the first interrupt in the whole thing is the reset signal. It is called by default when you power up your machine, and it invokes main. That makes sense? Right? That's the mechanism by which your controller loads main when it starts up. It starts up in such a condition that it automatically triggers the reset interrupt which loads main. Make sense? So, priorities then. Lower numbers have higher priority. And I know it's like back to front, but so negative numbers have the most priority. Generally speaking, the negative priorities are reserved for these system hardware internal interrupts. The 0 and positively numbered interrupts are, those are reserved for the external interrupts. Things like signals coming in from timers. With me so far? Good. Any questions? Good. Yes. So this works because the program counter is initialized to 4, which is the first address in memory after the first one, which contains the interrupt vector table entry 4 reset. Good. You can see like hard fault handler, memory management handler, like seg faults are in are in these guys, right? Good. Yeah. I don't expect you to memorize all of them because there are 256 of them. I wouldn't expect me to memorize them. So this is a view of the various interrupts that you have available. So it's important to note that although 256 interrupt slots are available, depending on what board you have, more or less of them will actually be used. The ones that are unused, generally, you'll see reserved in their slot. So the boards that you're using actually, I believe, only have 42 external interrupts that they actually register. But that's assuming that the board you have is the same board as being referenced in the textbook, and it might be like a slight variation on it, so, you know. Actually, you have your lab kit.
Yeah.
Could I see your board?
Okay.
I want to see if it's the same model number. Yeah, this is, okay, so it's a slightly different one. The one referenced in the textbook is the STM32L4, and that's the F429. So probably a slightly different number of interrupts. It doesn't really matter. It was kind of just for interest's sake. Anyway, so so there's a standard for these Cortex processors called CMSIS, which I believe stands for Cortex Microcontroller SIS. I don't know. But anyway, it's the standard. All of the manufacturers of Cortex boards have to follow the standard. I've explained to you how hardware standards and ISAs work, right? Did I? Did I not?
I don't recall.
Okay, well then, all right. So this is how hardware manufacturing works for processors particularly, right? So there's a standard which is done by a company, right? That standard is licensed by manufacturers who must build their boards they must build their board to the specification. But the company that actually manufactures the board and the company that controls the specification are generally two separate companies. Intel is kind of an interesting thing because they both make the standard and the chips. But so yeah, essentially, when they make one of these things, it's called an ISA, which is a instruction set architecture. So it defines various things about the chip, what instructions are included, the manner in which memory is mapped, all of this kind of stuff. If you were to look, you would be able to find a standards document that contains all of this information. Of course, it's boring to read because it's a standards document and the slides are a little bit flashier, although not much. So, you know. And generally speaking, the other thing is if it's a proprietary standard, then you have to pay, hundreds of thousands of dollars in order to be able to look at the standard, which, of course, I know I can't afford. So the RISC-V is an open source ISA. So if you want, you can go on your laptop and find the instruction set architecture for RISC processors. Anyone can make that chip because the standard is open. RISC-V is actually starting to gain some ground as well. It's gonna be giving ARM some trouble in a few years, but until such time, ARM is still king of the hill. at least when it comes to embedded systems. But yeah, so anyway, the standard defines all of the internal interrupts with negative numbering, but in the Cortex-M, like, negative numbering doesn't really work, and you want to maintain like the relationship between the numbers, and basically you add 16. That's a long way of saying you add 16. So, yes. Yep. So, so the stacking and unstacking procedure. Once again, we have our user program, which enters the interrupt handler and then goes back to the user program. So it's going to get a little bit complicated again. So there are actually two stacks. I know we've been like laboring under the impression that there is one function call stack in the system, but it turns out that there is actually two. They are called MSP and PSP, main stack pointer and process stack pointer. The purpose of having these two stacks is it's essentially in order to enable operating system support. So the main stack pointer, generally speaking, is reserved for kernel type operations and other like operating system stuff. Process stack pointer is used for like user programs. So this is like the architecture that enables the operating system on your phone to not have to share a call stack with the your particular instance of Crossy roads. Whether or not you're in MSP mode or PSP mode is determined by a bit in the special register, the special purpose register. So obviously you only have one processor, unless you have more than one processor, but let's not go there for a moment. Your program counter needs to know whether or not it's in MSP mode or PSP mode, because it needs to know which stack it's stacking things on, right? So there's a control bit that's actually in the special purpose register of the CPU that tells the program which mode it's in. Any questions about that? Have I completely baked your noodles? Yeah. You're allowed to ask general questions as well. Yes?
So how are you able to use both of these at the same time?
It's not so much that you use, like, you can only be in one program, like you can only have one program execution going at a time. It's more like if it allows task switching, right? So, you can imagine your version of your Crossy Roads program has all of its own functions that it's executing. That's it's doing its own thing. But like you may also want your cell phone to have various processes related to the telecommunication aspect of your cell phone. You may want that to not have to share a stack with Crossy Roads because Crossy Roads uses quite a lot. I don't know if it does, but so it's more like a separation of concerns type design feature because obviously you can't process both at once because you've got one processor. Make sense? Question?
So can MSP and PSP be like in any register? Like, can you swap between them for any register, or is it just register 13?
Oh, so these are stacks, right? So
Which stack each register is working with?
no, it's like overall mode. There's only one bit that controls it, so it puts the entire processor into either MSP or a PSP mode. Good questions. Any other questions? Yeah.
So the interrupt is what's responsible for switching it, or
Well, as we're going to see, actually that plays into the next slides. So as we're going to see, handling mode is kind of something, it's something else from either of them. The interrupt, this is like a long architectural diatribe basically to say, give you a piece of information that may or may not be useful, which is if you're in MSP mode, then the stuff that gets auto-stacked onto the stack gets stacked onto the MSP stack. If you're in PSP mode, then it goes onto the PSP stack. That's essentially the point of this, but it's interesting to know that there are two stacks. So, yeah, essentially. Good. Yeah. So, essentially, if we have either of these stacks, so, all right, MSP, PSP, main stack pointer, processed stack pointer. The SP is stack pointer. What does the stack pointer do? It points to the current stack frame, right? So when we load, when we stack our existing, our register information onto the stack, we sort of start off at the old stack pointer. We load all of the data we need. The stack pointer now becomes whatever this memory cell is, whatever the address of this memory cell is. And during unstacking, we take each of these things out, load them back into their respective registers, and return to our old stack pointer value. Cool? This is a lot of very technical information. I'm surprised any of you are following this at all, including myself. So, yeah. Good. So the control register, SP select is the actual bit that is flipped to represent either MSP or PSP mode. Oh gosh, I forgot what FP stands for. Oh shoot. I should write myself notes. All right. Let's see here. Wow. Shoot, I had it too. God damn it. Function pointer, maybe? I think. At any rate. So you can also set whether or not the thread has privileged access using another bit there. If you want to modify these, you can. It requires well, it doesn't necessarily require assembly level instructions, but this is what it looks like in assembly. But yeah.
So,
yeah.
FPCA stands for floating point context active flag, according to the textbook.
Floating point context active flag. Floating point?
Yeah.
So we haven't been talking about floating point at all thus far. This seems out of context. I'm not criticizing you.
It's just a diagram taken out of the textbook.
Yeah. What page?
600, I think.
600?
Yeah.
What?
Section 23.1.1.
23.1.1. 23.1.1?
is what he said.
Jesus Christ. Floating point context active flag, yeah.
I think it just turns on the coprocessor.
Indicates whether the processor has executed any floating point instructions.
I think that the ARM chip has like a coprocessor for floating point, so it just turns that on. I
Yeah,
think.
yeah, that makes sense.
Yeah.
Yeah, floating point processes are often accelerated in an external chip, just because they tend to take a long time. Yeah, okay. All right, next slide. So,
Yeah, it's so weird that it says that.
So, if we're in MSP mode, we are always dealing with a level of privilege that is privileged. Otherwise, it depends on whether the privilege has been enabled, but MSP is always privileged. So that's okay. That's good. All right. Right. So, yes.
So in this case, when you're adding something to this, okay, that's what.
Which slide are you talking about?
When you're stacking, are you adding it to the front, or you're moving it in front of the memory that's currently existing on the stack corner?
Yeah, so, where's the chalk? There it is. So, remember that our stack memory, remember how the stack memory worked from topic 1, right? We've got our memory region. So within the data memory, our main stack frame is at the top, and the stack grows down towards the heap memory, which is growing up, right? So it actually will go as it has been illustrated in this slide. You will be starting here and growing down that way, right? And then, of course, popping back up. Make sense? Question?
What actually is the control register? What does it do?
Well, it's keeping track of information like this, right? Now that's a high level question, isn't it? So, like the front half of the control register, I believe, is the NZPC bits. I think it's NZPC. Those are the bits that are polled by the branching instructions to see whether the last operation was like a greater than or a less than, right? It reads those bits to determine branch jumping, right? So that's what part of that does, I think, if I'm getting the right register. But it's like various little bits and flags that you need to control the execution of the processor, you know? It's like, it's one of those interesting ones where it's like, you know, you can look at like 2 bits and go over by 4 bits and you're looking at a completely different function of the processor. So you really, like, it's really bit by bit that you have to go to determine what the actual functions are.
So the 31 to 3 reserved, those would be the NZ bits? On the next,
Let's see here.
yeah.
Yeah, like, reserved can sometimes mean reserved for other purposes. I don't know, maybe it's, am I getting that right? Is it, I'm pretty sure it's 13. Pretty sure.
13 is just
Is it?
stack point.
Wait, no, I'm sorry. The control register is what we're talking about. Yeah. Well, anyway, we'll figure it out tomorrow, right?